Okay, everyone, we'll go ahead and get started. So for those of you who have just joined, my name is Chloe Johnson. I'm the lead aluminum materials engineer here at Elementum 3D. We're going to go ahead and kick off this webinar, and I'll get started by introducing a little bit about us at Elementum 3D. Hey, Patrick, I'm having trouble advancing the slides.
Yeah, you're good to go. I'll remove you and re-add you.
Okay. Okay, let me try again. All right, awesome. So at Elementum 3D, for those of you who aren't familiar with us, our mission is to basically supply unique metal powder for 3D printing, R&D, and new metal powders and applications. So really what that boils down to is we want to expand the materials library for AM. And so we're going to talk a lot today about supply chain and materials for AM. And really our goal is just to make those alloys available for everyone. So today we're going to focus on some of those different alloys that we've developed, that we've made available, and really talk about how that's been able to help the AM supply chain. Okay. So just a note on some of the different material classes we work on. We have many different aluminum alloys. For those of you who are familiar with our materials, you've probably seen some of our aluminum materials out there. I'll be talking a little bit to these materials, but we also work on particularly nickel alloys, copper alloys, refractory metals, and we've done some work in steel as well. So I have two colleagues here today, Ben Rafferty, who will talk a little bit about our nickel materials and what the work we've done there. And then also Hu Chun Yi is going to talk a little bit about our copper materials. So we just want to chat about these materials and how we've been able to utilize them to help with some of these supply chain issues in AM. So jumping right into our aluminum materials, for those of you who may not know, aluminum is not something that's easily printable off the shelf for additive manufacturing. There are a few select casting alloys that, when additive kind of first got started for metals, we were able to print outright. Many of you probably are familiar with ALSI 10MG, right? However, if we go to use some of our wrought materials that are higher strength and particularly precipitation hardenable, things like 6061, 2024, 7050, we can't really take these base powders and print with them. And the reason this is that we have these columnar grains, like you can kind of see in this image of the tensile bar here, those long kind of columns that are basically going up the tensile bar there. And you can also see that in the colorful grain map where we're following the build direction, and we can see those grains growing upward in that material. Basically in between those grains, we tend to have hot tearing or solidification cracking occur, and so we can't really use this material as is off the shelf. And so while these materials are great, we want to use them, this kind of hurts the supply chain that we can't just use these off the shelf. And so we started by basically using our technology for these materials in particular to develop more aluminum materials that are printable for AM. How we did this was using our reactive additive manufacturing technology, our RAM technology. If any of you are familiar with our materials, you've heard this RAM acronym before. Basically how this works, we started really in laser powder bed fusion, but we kind of work with any AM process that utilizes powder. So you can see a schematic of our LPBF process in the center here, where we have basically our powder feedstock on the far right. We have that spread over by a recoder to our build plates, where our part is lased in a 2D cross-section layer by layer until it is a solid 3D part. But basically our process starts with the actual powder feedstock. So we have basically that base aluminum material, we add some reactive precursor particles that are about a micron in size. We might have one or multiple of those that then when they are lased in the melt react together, either with each other or with the melt to form particles that serve as nucleation sites for our grains. So we get rid of those large grains with that solidification cracking, and instead we have a refined microstructure with no cracking. So what this allows us to do is take that off-the-shelf aluminum alloy that you're used to using from a wrought material and basically take that grain structure that's very large, columnar, and isotropic with cracking and refine it. So you can see on the right here, that refined microstructure, particularly with that EBSD map, where those grains are colored according to orientation. And so the idea is that we can now start to utilize these materials off the shelf by using our additives and have more aluminum materials that are readily available for AM. So not only can we use these to just refine the microstructure and get rid of those cracks, we can also use these to basically play with the amount of precursors we're adding to our material to start to get into composite-like properties, or maybe to have a little bit less residual particles in our material because those particles don't fully dissolve. So this slide really highlights that. You can see on the very far left, the material, what it looks like if we print with no precursor particles, versus as we start to add a certain amount of our RAM precursor particles, we refine the microstructure further. In fact, we kind of see the peak of that refinement with our 2 volume percent, our RAM2. So many of our products are RAM2, but we can basically add more particles beyond that to have kind of a composite or particle strengthening phenomenon. And so we see in our RAM10, while we're not necessarily refining the particles further, we might be able to take advantage of those composite properties. So this allows a wide window for different materials we can provide to meet different applications. So just a note on properties, our whole goal is to try to help provide alloys that, you know, are readily available for everyone, but we want to make sure that you know, we can use them kind of in similar design areas as like our wrought products, right? So on this slide, you can see a comparison to particularly the wrought legacy alloys that, you know, basically form the base of our material. And what you can see for 6061, RAM2 and RAM10, and then 2024 on the bottom, RAM2 and RAM10, that we achieve comparable properties. So you can see our yield strength for 6061 and tensile strength are comparable. Again, this is a minimum versus a typical value, so not exactly the same exact value, but comparable. Similar for our 2024. And so this allows us to be able to print materials that we're used to working with in conventional manufacturing. So finally, another note on mechanical properties. A lot of you have probably heard about the concerns of additive and fatigue. So one of the big things we do when we develop a material is we want to take a look at that fatigue behavior and compare to conventionally processed materials. And what you'll notice in this slide, particularly for 6061 and 7050, is that we get fairly comparable fatigue performance compared to the conventional MMPDS volume 1 data. And so you can see that the green dots would be our material on these curves, and the black dots would be those MMPDS materials. We also have some materials that are a bit unique to our design process, such as our A1000 RAM10, that compare well to other additive materials, and in fact may actually perform better. Apologize, I'm having some trouble advancing our slides. There we go. Go back one more. Patrick, do you mind moving it back 2 slides? There we go. So one material that we're working on at the moment, kind of an area where we have not quite filled in the gap of the supply chain, is some high strength aluminum materials. So these would be high temperature, high strength, and particularly looking at the aluminum, silicon, vanadium, iron system. And the main reason we wanted to consider this is if you look at these 2 figures on the right, the top shows our yield strength with temperature. These materials allow for us to maintain a high yield strength at higher temperatures. So we're going to be particularly talking about the material that's kind of that dotted line at the top. Also, these tend to have good creep resistance for aluminum materials, so another high temperature property. So on the bottom there, you're seeing the creep elongation versus time for different temperatures. And we're going to be talking about the solid circular dot that's kind of on the very bottom right of that graph. So knowing about these materials, we wanted to take advantage of this for AM. As we know, many people have some high temperature aluminum applications, particularly for automotive. And so we decided to develop particularly 8009 as part of this aluminum, silicon, vanadium, iron system. And the great thing about these materials is that they don't need a heat treatment, so we can use them directly out of the printer. So this was another space where we said, hey, we can take this material we know well from conventional processing, we can translate it to AM and increase the number of materials that are available. So the first thing we did is we just took a look at the off-the-shelf material, right? Because if we can print that successfully, that's excellent, but we knew that was probably not going to be the case. So you can see here the 8009 raw material, or off-the-shelf material to the in that picture on the top and the very left side of that picture, versus when we put our additives in this material and made it a RAM2 material. And that microstructure you're seeing on the bottom is actually the RAM2 material. And so we were able to eliminate cracking, which in this case was actually more from residual stress than necessarily solidification cracking. But that residual stress basically caused those cracks because of the solidified microstructure. And so with our additives, we were able to change that microstructure and prevent that cracking from residual stress. And what happens is we have all of these little particles, as you can see in that image, that are stable at high temperature, and that gives us that high temperature strength that we're looking for. So we do some initial data on this material. We're continuing to develop it, but we did find that compared to the raw 8009, so that's what you're seeing kind of on the left there in the room temperature tensile data, that we were seeing that we were getting somewhat comparable strengths to the raw data, but particularly looking at the elevated temperature tensile, we were really seeing that we are continuing to keep that yield strength fairly high up to high temperatures, whereas some aluminum alloys at higher temperatures tend to start to basically drop off around 250 or 300 degrees C. So we're very excited about this material. We want to continue to develop it to fill in this gap in the supply chain. So with that, I'm going to go ahead and hand it off to Ben Rafferty, one of our other engineers here at Elementum 3D. So take it away, Ben.
Thanks, Chloe. Hi, I'm Ben Rafferty. I'm the lead materials engineer for our nickel superalloys and refractories at Elementum 3D. I'll walk you through kind of what Elementum 3D offers material-wise, and kind of like the idea of like why we care about nickel alloys and how recycling of AM powders can be very influential in the nickel alloy world. Like people aren't familiar, nickel is used in everything from your pocket change to aerospace industries, with most commercial aircraft using about 50% of its weight in super alloys or nickel alloys, and a big one being 718, and taking up quite a lot of the readily available super alloys that are actually manufactured. And as we continue to need more and more of this industry, more and more need for these alloys to keep the modern world moving. And so much that in industry, or in the call out from the Department of Defense, is looking for more domestic sourcing of nickel alloys. And currently the US only really has one nickel cobalt mine they can utilize. So you see that a very robust need for recycling of these alloys is crucial. And at Elementum 3D, we could most certainly see how, in partnership with Continuum, when they present later on in this presentation, that we can have this cyclical effect of E3D printing a material, supplying our scrapped or unused material, it getting repurposed into new, more quality feedstock from a recycled source, and then Elementum adding its RAM inoculation systems to our nickel alloys. And we've had, from the research that we've seen with the, and success from the alumina alloys, we wanted to put these to use in our nickel alloys. And we've had great success in developing 230, an alloy 230 equivalent, or Haynes 230 equivalent, and a 625 RAM2, which is a more enhanced 625, as well as partnering with NASA to commercialize and mix their GX810. And we currently have pilot projects trying to offer a 718 RAM product for industry as well. With our success with the Navy SBIR for alloy 230, you're not familiar with this, in laser powder bed fusion, Haynes 230 or alloy 230 suffers greatly from solidification cracking. And through the introductions of our RAM constituents or inoculants, we're able to preferentially create nucleation sites and heal the solidification cracking that happens, and then thus making a more robust and high performing alloy 230 for additive manufacturing with superior creep strength and mechanical strength for this material. With this material, I want to draw your eyes to the graph in the left bottom corner is our creep results from this, performed by the Colorado School of Mines, and the standard material just being AM alloy 230 compared to different creep rates of our RAM 230 greatly overcomes that and becomes more very close to a commercial product that Haynes International might offer from a rock billet. And just to give more understanding to that, in mechanical sense, we're able to, from eliminating that microcracking, to greatly increase our strengths and our ductilities at temperature at a industry of 760 C. And we see an increase of elongation by 73%, and 35% in the Z direction, keeping this material, showing it that it has quite a bit of isotropic properties as well. And then moving on to kind of some of our more recent successes is 2 years ago or so, we acquired a research license to mix GRX-810 for NASA, and try and develop new processes into introducing Y2O3 and coating it properly to make a usable product for this high performance medium alloy. In this image, you can see we have some SEM images. On the top, we see the commercial, the alloy provided by NASA, and just getting an idea of how much yttria we can coat these. And then on the bottom is using our mixing technique at Elementum 3D, we're able to not only coat the GRX-810, but also coat larger quantities of it. And we not only have we been able to show that on the powder side, we were also able to do that printing as well. And with some more microstructures that we're showing here, just to kind of show you on the left side, we are what an uninoculated or coated Y2O3 might be, an uninoculated GRX-810 would be without yttria. You get after HIP, you get a lot of recrystallization you don't know. You add the Y2O3 from what NASA did in the middle, you keep those grains nice and refined. And to give us here at Elementum a check to see that we are also still performing and not getting recrystallization, you have our product on the right after our high shear speed mixing. And with that, it just gives us more confidence that we're still making a product similar to what NASA is offering, and that is what is shown very successfully in our mechanical testing. E3D tested 3 separate mixes that we did of both yttria and the nickel cobalt chrome to make GRX-810, printed both the NASA supplied material that they were mixing and comparing it to their results. And when we look at the differences between here in the dark blue on the right, where we see NASA's results, and then what we were able to recreate with our EOS M290, we see a slight decrease in strength, but comparatively from where we started without, on the left, without any yttria in the system, we greatly improved the strengths, and our strengths are very comparable to what NASA's material was and our material in the green box circled. So seeing yield strengths and elongations very similar to what NASA was showing, with about 20% elongation compared to 15% elongation, and you can likely see like 105 to 106 ultimate tensile strength. And all these were tested at a certified lab at PES, and at least 3 samples were tested at very high temperature at 1093 C. And we should be very close to offering this as one of our products here at Elementum 3D. And the next material I want to talk about is what is, come on. Patrick, it kind of, it's not forwarding the slides. All right, thank you. And then kind of our workhorse nickel super alloy that we've been offering for the longest time has been Elementum's RAM 625, Inconel 625 RAM 2, and we offer it in 40 and 60 microns. We've been able to improve strength from basic, from standard Inconel 625. We maintain a high level of strength. We can print quite a bit of complex geometries, kind of found just, and we're able to maintain a crack in fairly dense microstructure. And to kind of give you guys more of an understanding of where all three of these are compared to where 718 kind of lays in industry, where our Inconel 625 is very comparable at temperatures at ultimate strengths to 718, where the GRX 810 and 230 kind of more on the lower end as temperature increases, but they are able to show that with these materials, we maintain a high level of elongation with these materials and don't suffer from the shortcomings that 718 might have with offering both hulled solution alloys and the GRX 810 for very high temperature applications. And at Elementum 3D, we're very much researching more and more into the super alloys with our project with the Navy going and looking at more gamma prime alloys such as 738 and MARM 247. But with this, these are kind of my final thoughts on kind of presenting you the super alloys. My colleague, Dr. Huchan Yi, will be talking to you more about copper alloys.
Next pan. My name is Huchan Yi, and I'm a material scientist here at Elementum 3D, and I'm working on developing copper and copper alloys. And I have a few slides. Just wanted to address the issue of how we address the supply chain when it comes to printing copper and copper alloys. So at Elementum 3D, we focus on either both pure copper, we call it commercially pure copper, and copper alloys. So on this chart, this was published by NASA, that shows the strength versus thermal conductivity of pure copper and typical copper alloys. So for commercial pure copper, theoretically, this is for thermal management applications, is utilized its high thermal conductivity. Theoretically could go to up to 400 watt per meter K. That's very pure, 100% pure copper. But in reality, for commercial pure copper, you always contain small amount of impurity, typically of 0.5% or less. So the number is typically about 360, as shown in this chart. So later on, I will show that Element 3D, so our copper, we can print samples with conductivity over 360. Typically, we have 370. So when it comes to copper alloys, there are numerous copper alloys, a lot of bronzes, and those we don't, there's no difficulty printing them. So I'm not going to talk about those, but I'm going to talk about the alloys that's really difficult to print. There's a supply chain issue. In particularly high-strength, high thermal conductivity alloys, such as GR-COP 4284 that was developed by NASA. This alloy has high conductivity and also maintains its high strength at high temperatures, and is used for rocket engine, for example. And there is an intermediate grade like copper chromium or copper chromium zirconium alloy, which has a medium strength. And Elementum 3D, we are focusing on those two kinds of alloys. So I'm trying to move to the next slide. It's not moving. Patrick, do you think you can move it for me? Okay, there we go. So when it comes to printing conventional pure copper, it is difficult. The reason is really because it has a high conductivity and it has very high reflectivity. So basically, the laser energy is reflected off. In other words, absorption is very, very low. And so we at Elementum 3D, we tested, all major copper producers worldwide, and we found the same problem. And you can't use high energy because high energy printing will give you other problem like K-holing, and you will have reduced optical life for the laser, and basically you won't get a high density. So if you look at this equation, the relationship, it tells you only have two options. One, you reduce the wavelength, change the color type. The other is reduce the conductivity of the powder. So the first strategy, reduce wavelength, is already commercial green light, green color laser out there. But for the ordinary laser printers, at Elementum 3D, we focus on changing the powders. By reducing the conductivity of the powder. So you heard earlier from Chloe and Ben. So we developed RAM technology to make aluminum and nickel alloys from the shelf powders, non-printable, printable. With copper, we developed a different technology with the same goal, basically make the unprintable from the shelf copper, pure copper, printable. So we developed properly the process, basically to turn commercial copper into feedstock with increased absorption coefficient, so that we're able to print high density coppers. Next slide. Okay, so here this slide give a summary of the copper powder feedstock we developed. So those are the typical printing parameters, and the density we are comfortable we can print over 98%. If you don't process it, typically by 80s, somewhere between 80, 85, depending on the manufacturer, and also even the same manufacturer, depending on the lot they produce. But once we process this powder, we can consistently print over 98% every time. And the thermal conductivity is shown here on this table. about 370. We tested the multiple samples, and electrical conductivity as printed is about 85 to 88%, and after heat treatment up to 95%. So if your application is really you want very high, even higher conductivity, you heat it, we found it's over 98% RACS is achievable. And this is hot temperature testing data, semiconductor data. Here shows us a part we print for commercial customer. So move to next one. So let's talk about copper alloys. And so copper alloy, we're focusing on, for example, GR Cup 42. This is a chromium and niobium alloy. So basically, you have a 4 chromium atomic percent and 2 atomic niobium. So right now, this powder is produced by atomization. So you have to melt at very high temperature, typically 1800 degrees Celsius, and atomization, fast cooling. So and then you can form small size dichromium 2 niobium compound with a mark structure. So what I want to point out here is that the quality of this product, there are quite a few commercial manufacturers to make these powders, and not every manufacturer is the same. The quality really depends on the manufacturer, and we evaluated quite a few of them, and NASA also evaluated some of them. This table actually was presented by NASA. They evaluated 8 manufacturers, and you can see basically it very varies because the quality of this alloy depending on the amount of compound forms. So on the average, they are getting about 86% this compound. Theoretically, should be or form 100% of this compound. Then you have elemental chromium and niobium didn't form that compound. So some manufacturer form higher this concentration of a compound, some manufacturer has lower. So you have a higher concentration amount, then the strength will be higher. For example, this is a mark structure. You can see the background is not that clear, but it's just some small chromium niobium compound. But you can also see those white, those are unformed, unreacted niobium. Now also some dark formed chromium. So the biggest problem issue with GR Cup is that we found not only quality is inconsistent, also we found it's expensive. And if you ever try to order this, the lead time is relatively long. So we at Element 3D, we decided to develop something that's similar. So so we name it high operation temperature copper hot cup, and we have achieved some exciting initial data. And so the goal here is that we're going to have this powder mixture. Once printed, will have a comparable or even higher properties than the GR Cup, and yet the will be a lot cheaper, and it won't take a long time to get it. So just stay tuned. So we'll release this material in the near future. Move to next slide. So finally, this slide shows the summary of what we offer on copper, and you can purchase order this commercial pure copper powder from us. We call the AM Copper 100, and we guarantee it's high printability and good performance. And hot copper powder is coming hopefully soon. And we also provide printing services on commercial pure copper using our AM Copper 100, and also printing other part using currently GR Cup 42. And of course, in the near future, once we develop that hot copper powder, we'll use that powder to print part as well. I think that's the last slide from me. Thank you.
Yeah, thank you, Hucheng and Ben. So we're going to switch gears and hand it off to Continuum. Specifically, Rob Higbee is here. Apologize, Rob. To tell us a little bit about Continuum and what they do. So Rob is the CEO at Continuum. He's been there since April 2024. And he has a lot of experience in aerospace, defense, advanced manufacturing. He previously served as an executive partner at AE Investors, leading the aerospace and defense investments and advising Velo 3D. He founded and led Turbine Aero and held a senior role at Standard Aero and GV Aviation. And so he's definitely got a lot of expertise in aerospace. So we're really excited to have Rob here to speak to what Continuum's up to. So Rob, I will hand it off to you. Thank you for being here.
Thank you, Chloe. And let's move over to the slide there. Just want to say thank you to Elementum 3D for their partnership, both today, so that we can tell this story together, but also in the industry with respect to things we're doing in powders. Continuum Powders is a very natural partner for Elementum in the sense that what we're trying to do is enable a more sustainable, higher quality option of what they're bringing to the market. And so that's what we do in a nutshell is participate in the multi-billion-dollar industry, both customized powders like Elementum, but also more generic powders like, call it Inconel 718, 625, Thai. The only difference for us at the end of the day is that we are taking our feedstock from scrap. That could be powder that's unused in a machine. That could be failed builds or test builds, build plates, any form of waste that takes place in a more traditional manufacturing, like machine turnings, or also anything that's removed from the field, like fan blades that might come out of an industrial gas turbine engine, aircraft engine, whatever it may be. In a nutshell, if it's in that base alloy that we are trying to turn back into powder, we want to use it. There we go. The reason why we exist and why we think there's such a large future is because of the core problems that we're seeing in the industry today. And as an individual who doesn't really have a sustainability background, it was interesting when I started learning more about Continuum, in that I initially said, oh, this is just another sustainability play where, people who are more focused on greenhouse gas reduction, we're trying to promote that cause. Kind of like you maybe see in the food industry when people are promoting organic, elements for healthier farming or whatnot. But the reality is that metal really never changes its chemistry. Obviously, it can change some of its properties, but that core base alloy, once it's extracted from the earth, can technically be used over and over again, really only needing some core treatment to make sure that the physical properties are met to from whoever the OEM or manufacturer is. And so taking that as sort of a basis, we realize that metal powder and metal in general is not a sustainability play just to go green. It's actually a sustainability play to have a more efficient and more cost-effective solution. And so that particularly times well with a lot of the supply chain disruptions that you're seeing in the marketplace right now. A great example is titanium. Titanium is typically procured from countries like Russia, Ukraine, or China, all three of which are sort of under duress. And so it's very inviting for our industry at large to consider recycling, not only because it's very difficult to get some of that ore from mining companies, but also because there's so much extra waste, so much extra scrap that's available, all which is actually the most perfect form of metal ore or feedstock that we can then put into the right form factor and then atomize in one of our foundries that we have all over the world. The high costs of metal powders are typically, because of two core things. One, just the processing, meaning the atomization of making those powders, but then also the procurement of that ore. And when you have so much waste of that pure ore that's available, and a great example might be, you know, a watch that a lot of people have, that's got 90 to 95% waste in a traditional machining operation that goes on the floor and then gets wasted at the end of a manufacturing day. That's all perfectly good titanium, or in some cases nickel, that can be reused if you can take that and put it back into the form factor that the advanced manufacturing industry, the additive manufacturing industry, obviously wants to consume it. Yep, looks like we're moving around a little bit here. So if you look at how we achieve that, it's very simply perfect. Let's stay here on the solution slide. So look at how we achieve that. It's essentially through a foundry that we've developed, which is our intellectual property, which is set to be scalable, much more cost efficient, and then absorbing and accepting of less traditional feedstock, if you will, namely scrap, which there's much more of globally than there is core ore that we're, you know, constantly, you know, mining from mountains through various mining companies across the globe. The way we do that is as simple as this graphic tries to describe, which is we procure that feedstock through any of the sources that I mentioned a moment ago, put into a form factor that allows it to be atomized. And for those that don't know what atomization is, it's basically the process of putting a lot of heat in the form of a flame and then various gases over a metal solid, which then allows it to be atomized into powder to literally any set of specs, whether it's spherical shape, whether it's morphology, whether it's density or flow, that then obviously hits the spec that our customers need. That's obviously then used in any one of the advanced manufacturing applications that we've talked about today, typically laser powder bed, but also applicable to DED, MIM, any of the spray like laser cladding, flame spray, and also hipping you know, applications, all of which require massive amounts of powders. That's sort of the build step, if you will. And then after that, that becomes one of several waste streams that we very enthusiastically want to remove with our customers, such that we can turn that back into great powder for our customers, whether it's a standard alloy, once again, that we've talked about, like a Inconel 625, or something we've done on a more custom basis, for example, through our partnership with Elementum 3D. So this is a great example of sort of how we do that and what core alloys we look at. And we've obviously got a very engineering and intelligent group of folks on the audience today. So hopefully you see most of the alloys that comprise literally sort of 50 to 60+% of the industry. A lot of nickel, a lot of tie, and then, you know, buddings of copper, which are really starting to make their way through the industry. Obviously, you know, tons of aluminum as well. What we do, though, is also a large series of custom alloys, usually through a partnership through Elementum 3D, or something we might be doing proprietarily, usually more of a micron size with one of our customers. And what we also try to do at Continuum is not just be the highest quality, the most sort of sustainable, focused, and the most cost flexible, but we've also really tried to bring an element of higher touch and better service levels to the industry. So when we're partnering with Elementum or a service bureau or an additive machine OEM or a core, what we call strategic OEMs, maybe a Lockheed Martin or a General Atomics or something like that, what we want to do is deliver this element of what they do in their business in the most sort of service-friendly manner. So the first is just what we call OptiPowder. That is our portfolio of solutions, including custom solutions through partnerships like Elementum. That is us just participating day to day in the metal powders industry. In this case, as a provider that provides a sustainable version of that powder. Where it gets more exciting and candidly where we really dig our teeth in is when we begin more of a circular metal economy approach. And what that means is we're working with core partners to take their scrap, make sure that it's, you know, the right feedstock. We oftentimes will treat that, obviously have to ship it to one of our facilities. And then what we're doing with that is then being a circular metal economy partner where we take their scrap from a repair facility, could be from the additive facility that has, you know, spare powder, failed builds, whatever it may be. And then we say, let us take care of that for you. We will re-atomize that back into ASTM or whatever the spec is that the customer wants, and then give them back so they can use that in any and all of their additive manufacturing or advanced manufacturing applications. And so it's very much a circular metal economy that we sort of call off-site, because we're taking their scrap off one site, atomizing it, and then giving it back to their additive fleet such that they can have their powder supply come from the very scrap that they were getting rid of from a different part of their company. And then finally, where it becomes nirvana, and this is where I think the future of our industry really is, and you're starting to see a lot of this as the team from Elementum has already pointed out, in both the Department of Defense and Department of Energy, but also with major sort of global conglomerates that are producing tons of metal waste and also need tons of metal powder. It's a circular metal economy in a co-located fashion. And what that means is similar to the way Xerox used to have printers that they would put on site at various companies around the world. We're beginning to put our foundries onto a customer's facility and then having basically a recycle, atomize, provide powder managed service, where we're simply just providing that powder on a per kilogram price and then run all the logistics and all the procurement needs such that our customers and partners can focus on building great parts for their customers. And we can obviously focus on providing that powder solution. The next slide here. So not a surprise to anybody, but all the same sort of metal powder, advanced manufacturing industries and users are where we naturally play. And what we want to do is really partner with sort of call it three types of next generation thought leaders. One is the folks who are on the front line designing the next great alloy or super alloy like Elementum, which we're very grateful for that partnership. They sort of define what it may be, and then we're the ones who can obviously procure and manufacture that, but in a much more sustainable manner. So the next would be then the additive machine OEMs, where they have particular elements like an EOS, an SLM, a DMG Mori, that they need to make sure that their powder needs are met to provide the best parts with the best properties. And then finally, it's the service bureaus and the OEMs that obviously are consuming and building these parts for production. That takes place in any and all of the industries that you would expect. We've covered them all today. These are some examples of some of our core customers and folks we work with. And the parts that we're making are exactly what you would expect that anybody on the webinar today is obviously producing as part of what they're doing and or they're looking at with respect to going from a less traditional or a less forward-thinking form of manufacturing, could be forging or casting, into a much more efficient powder-driven advanced manufacturing solution. What is probably, I'd say, every time we go talk with customers and partners becoming more and more important is the sustainability impact that we're able to bring to companies. And it's quite phenomenal when you look at it, starting with quality, which I'll talk about here in a second, but also then call it price. And then most importantly, how customers can begin to go to market. And so the quality is very simply the ability that we have to have a back to melt birth record that no other sort of solution in the industry can really have. The way I discuss it with customers or partners is very simple. If you've got, for example, a MARM 247 fan blade that you need to run in one of your industrial gas turbine engines, and that has been BER'd, beyond economic repair, and a repair process, if we get a hold of that MARM 247 fan blade, which is maybe fatigued or timed out, there's no better pure alloy than that actual fan blade to then go create the same alloy now in the form factor of powder. So the quality that we see both based on our feedstock, but also our atomization capability are what is providing sustainability in this case that's coupled with the highest quality in the industry. When it comes to price, it's very obvious that we're both removing scrap from our customers and then returning that same base alloy almost as a refurbished or repaired product, but it's now in the form of powder. So if we're partnering with customers and with Elementum to use feedstock that is scrap, well, then naturally we're able to offset a cost that they have to get rid of that scrap, but then also use that to create the very powder that they need in their additive manufacturing applications, such that we're able to provide a lot of cost flexibility there in making sure that they're able to, get the most use out of this circular asset that never really changes its chemistry processes. And then finally, what's most important, I think, to a lot of our customers is we're finding that by partnering with us, they're achieving a more sustainable offering for their customers. And so if you look at any one of the additive manufacturing called service bureaus, what we're trying to do is partner with the ones that are true thought leaders that are now able to market to their customers that they're producing sustainably produced parts, against the rest that is maybe producing a less sustainable and probably higher cost part. So the ability to partner and bring this solution in conjunction with either OEMs or service bureaus or any of the additive machine OEMs that are obviously going in this direction provides a win-win for everyone. That's joining in this revolution. Go on to the next slide here. How we do this is through a network of facilities across the globe. What we show here is our Houston facility, which when we open it on the 5th of December, it's technically already open, but that's when our grand opening is, we will have the largest gas atomization metal powder facility in North America. This has sort of been what I would almost say 10 years in the making through companies like us and others that have made this switch to create powders via sustainability feedstock source versus a less sustainable mining option. And that is what we're going to be announcing in December, such that we're able to provide all the capability, all the output that's needed, not only for the global industry, but for a lot of the companies that require a US partner that might be working with the DoD or DOE that obviously are part of the customer base that we're serving. In addition to Houston, we also have our R&D and production facility in Cloverdale, California, which is where we were founded back in 2016. And then we also have a Singapore facility, which helps us serve the Asia-Pac markets, not just Singapore, but obviously Korea, Japan, and others, where advanced manufacturing technologies have really started to take off. In terms of our partnerships and whatnot, we wanted to be careful about which customers we put in for obvious reasons, but wanted to sort of highlight 3 key elements. One, we work with every major advanced manufacturing technology and OEM. That's sometimes reflected in a public certification. Other times we just do that through partnership, customer case studies, et cetera. But at the end of the day, most of the powder folks are all developing to a spec. That's what we're able to do. Hence, we're endorsed by every major additive machine OEM. And we've also been very active in any and all branches of government, both military and energy. And then we try and take a really strong thought leadership position with any and all of the industry associations that naturally are helping drive this revolution of going from traditionally mined ore to a more sustainable solution through reclaimed scrap. In terms of how to work with us, we're always ready to partner with Elementum, which is fantastic. That's where a lot of our custom solutions may come. But then we are also very eager to have discussions, provide samples of powder, provide samples, get samples of your scrap, and then turn it right back into powder. So if anybody wants to give us a few kilograms of their scrap, we'll gladly return it as ASTM spec or whatever spec you desire, powder, such that you'll be able to see how simple it is to begin turning existing scrap, which you otherwise are paying to get rid of or not getting a good value for, and then having that connected with any and all of your powder needs. I think we have one more slide that sort of talks and puts this all together. This is just a basic idea for those that might be working with us or might be working with Elementum, how sort of this partnership works, which is we want to develop any and all of the powders that are either directly a result of something Elementum's already built and or be the powder source for the next generation custom blends that they're creating, all of which can be done, as you can see here, in a much more sort of comprehensive way that's sustainable. And so the ability to work with either one of us is obviously how you would take some of those next steps. And again, just want to thank the Elementum team, not only for their thought leadership in the industry on really pushing the envelope on next generation alloys, but also for the work that we've been able to do with them and be able to tell that story here today. Patrick, I think I'll turn it back over to you.
Yeah, thank you, Rob. Very helpful. So glad to have you here and to be partnering with Continuum. So just a note, we're going to shift to a Q&A session. So please do put your questions in the chat so we can go ahead and answer those. But also just as a reminder, this webinar is recorded. It will be emailed to you in case you want to reference any of this information later. So please feel free to put any questions in the chat. We'll go ahead and get those answered. Okay, so our first question is, after use, what percentage of the RAM powder can be recycled or reused, or is this not recommended at all?
This is probably a question for me, I would guess. The great news is that in addition to the atomization of a solid into powder, we have several technologies which allow us to just be, what I say to the team, feedstock form factor agnostic. And so it's a great question, because what typically happens is you may atomize to a yield of, say, 30% on a good day, which means there's a lot of powder that probably from a micron size is not developed to spec. And or if it's something that's coming out of a machine that's been used 3 or 4 times, in the case of, say, tire, for example, that's been oxidized, and so it can no longer be used again. The great thing is that at Continuum, we have the technologies to be able to take unusable powder and then put that back into a form factor that we're able to atomize it such that it has a pure back to melt record. So the short answer is, other than yield that might be through leakage or bad use by an operator or something, it's actually 100% of the powder that either wasn't yielded out of our atomizer or wasn't yielded out of a advanced manufacturing, additive manufacturing machine. And we provide the services to pick that up from our customers that want to go into that circular metal economy. And we can also do that with the scrap that they provide and provide routine reports. So customers can say, gosh, I just sent you 10 tons of scrap, and you actually returned about 9 to 9.5 of powder. And that's a discussion we'd love to engage with customers on.
Yeah, thank you, Rob. So our second question is, have you guys experimented with combining your additives with a wet etching process to enhance conductivity in copper alloys? So I think Hu-Chen, this might actually be a question for you.
No, sorry. Okay, no, we haven't tested that approach because for the pure copper, we're already achieving very high conductivity. So I'm not sure whether that approach is going to further increase the conductivity further. But that is something that is interesting, though. We can think about it.
Yeah, thank you, Hu-Chen. And it looks like there's a follow-up question, but it has to do with our nickel materials. So this one might be for Ben. In one of your slides, you showed a comparison of properties for Inconel printed in EOS M100 versus M290. The mechanical properties looked higher from the smaller format printer, Is the decrease in material properties a process limitation, i.e. machine specific, or is it something else?
It's it is machine specific. The spot size on an M100 is much smaller than on an M290. When talking to NASA, they saw similar effects when they went from an M100 to an M290, but it does seem to help with improving creep strength, and we're still working on providing that data as well, moving to the larger laser spots size.
Okay, great, thank you, Ben. So next question, what are the prices of all commercial powders presented? Do you have a price list you can email to the attendees? On the Elementum side, I'm not sure about that. I'll have to check.
Yeah, I think on the Continuum side, it's very much just needing to know quantities, delivery times. Naturally, what we try and do is have the deepest partnerships possible. The more we can do that, the better the price gets. So we'd love to entertain that on a one-on-one basis, but hopefully very competitive and typically the way we try and engage on those types of questions.
Yeah, thank you, Rob. And actually, there's another question directly for you, Rob. This is from Rob Gill from MTC UK. Along with your atomization offer, would energy and other input data be available for environmental assessments of your products?
Yeah, Rob, it's a great question, and I'm glad you brought it up. So the core inputs that drive what I would call the product carbon footprint, the PCF, which our math currently shows that we are 95.7% less carbon emitting than traditional solutions. So any company that's looking to provide a needle moving, immediately implementable solution to their ESG strategy and that which their ESG leadership is obviously pointing on, this is a no-brainer. The way we get to that number is through the feedstock, which is 100% reclaimed. So that is, a major aspect to that. We are literally using the same scrap that was produced in some other application or repair process to obviously create the powder. But the other two core elements are, one, the transportation. So in the LCA analysis, the life cycle analysis would be the transportation of the powder from one location to another, which is why we obviously have the on-site solution. And then to your point, finally, the other two inputs are both the gas and the power to drive our foundry. What we've been able to do and why our headquarters is in Houston is because Houston is kind of the Silicon Valley for sustainability in the United States. And we have 100% carbon neutral energy sources through our partnership, all of which is coming off the grid. And then our gas is either recycled or the lowest sustainable option in the United States. So your feedstock, carbon neutral, power, carbon neutral, gas, it really just relieves the transportation that otherwise provides a complete carbon zero solution with respect to a product that you're already using anyway.
I'm on mute, sorry about that. Yeah, thank you, Rob. I think that is all the time we have for today. So thank you all so much for your attendance and for your questions. And thank you, Continuum, for being here and for sharing a little bit about your process and our partnership. And of course, thank you to our presenters at E3D for sharing some of our information. So thank you all. We'll send out this recording, and thank you for being here.
Thanks, everybody. Thanks, Elementum.
Bye, everyone.